In Thermochemistry 6, we're going to calculate the energy during a phase change. In the last video, we went through a heating curve for water. So we saw that there were several stages of that curve in which the water was undergoing phase changes and alternating between segments where we saw an increase in the temperature, at which point it was heating up the substance, and then we saw periods where the phase change actually occurred, in which, despite an input of energy, there was no temperature increase over time. So in this simulation here, you can see water in its frozen solid form. So here we have ice, and this ice is at negative 127 degrees. And we talked about in the last video as the temperature increased. Now here you can see we are just above the melting point of water. So at this particular moment where we are starting to melt, starting to overcome some of the intermolecular forces in water, in which now the molecules are able to slide relative to one another. As the temperature continues to increase, we're going to see this process of melting, this phase change occur. Okay, so heating it up now, we can overcome many of the intermolecular forces. So we are now at 36 degrees Celsius, and we can see these molecules moving as energy, heat energy, is put into the system. Now we're beginning to approach 100 degrees Celsius, and what do you observe? That some of the molecules of water are beginning to completely overcome. That's what we see here. And they're turning into a gas or steam during this point. We see some of them during this stage. Now at 106 degrees, we're at the enthalpy, the heat of vaporization is occurring here as we continue to heat the substance. Now beyond 100 degrees Celsius, we see energy, kinetic energy continue to increase, and now we see these molecules in their gaseous state in which all intermolecular forces have been overcome. And again, we could continue to put heat into the system to see the effects as the steam is now heating up. To revisit, these segments is very important as we now move into our one mathematical example. So we are going to calculate the heat required to change 50 grams of water at 25 degrees Celsius into steam at 120 degrees Celsius. So look at your heating curve and come up with a plan. Look at the segments of heat it up, break it up, so you know whether you're using Q equals MC delta T, enthalpy of fusion, enthalpy of vaporization, and how many times you're going to use the Q equals MC delta T. Because we want, in this question, to calculate the total amount of heat energy required for this phase change here. So our first step, where are we at on the graph? Well, we're at 25 degrees Celsius, which means if you look at the arrow, we're in the middle here of a heated up segment. So we're heating up water, which should make sense because at 0 degrees, that's the enthalpy of fusion, where water is beginning to melt and beginning to overcome some of those intermolecular forces. Here we are heating up the water. So think of the animation I showed you in the beginning of this podcast, and think about the molecular motion, kinetic molecular theory of these water molecules now beginning to move around even more. Now, if we're in the segment here where we have the temperature increasing linearly as a function of time, then we need Q equals mc delta T. So we're going to calculate the heat, and the value here is going to be in the units of joules. We have the mass of the water. We know the density of water, so 50 grams of water is 50 milliliters, but in this case, we're actually given the mass. We're going to plug that in. We know the specific heat capacity for water, and we are also given enough information to calculate the change in temperature, because our initial is 25 degrees Celsius, and at 100 degrees Celsius, during that phase change, we're not using Q equals mc delta T. That's where the line levels and the slope is 0 during the heat of vaporization. So our delta T is going to be 75 degrees Celsius. Now, we can calculate Q to be 15,690 joules of energy for that segment. Now let's look at the next piece here. The next segment is during a phase change of the heat of vaporization from D to E, that long segment, slope equals 0, during which the intermolecular forces are beginning to completely break up. We're going to use the enthalpy of vaporization, or heat of vaporization. I have the value here of 2.25 kilojoules per gram. Recall in Thermochemistry 5, I asked you to be able to distinguish and alternate between whether it's kilojoules per gram, as it is in this case, or kilojoules per mole. And to do that, you use the molar mass of the substance. Again, in this case, we're dealing with water. So the heat of enthalpy for the vaporization, 2.25. Let's do a little dimensional analysis here to convert this over. We have the amount, and the amount is given to us in grams. And when we do this, we end with 112.5 kilojoules. Let's continue dimensional analysis and go ahead and convert this into joules. So we have everything in the same units of joules, and again we cancel out 1,000 joules in a kilojoule. So now we've calculated the amount of heat energy between the segment DE, and the problem continues because our temperature is steam at 120 degrees. So we need to go to our next segment, which is from E to F, where we're at another heated up. So that means we're going to use Q equals mc delta T again for a second time in this problem. We're going to have our temperature, we know the amount, we know the specific heat capacity for steam. Be careful, that's a common mistake. We're going to use 2.01 joules per gram degrees Celsius, which is the specific heat capacity for steam, which is less than the liquid and less than the ice, and is indicated graphically as a slope that is greater than segments AB and CD. Okay, our delta T, or change in temperature, is 120 minus 100, which gives us a heat quantity of 2,010 joules. Let's go ahead and put that over with the other three calculations. And now guess what we're going to do to calculate the total heat required in this problem? We're going to add them up. When we add them up, we get a large number, 130,200 joules. Well, oftentimes we can calculate or convert that into kilojoules if needed. Divide by 1,000 or bump that decimal 3 spots to the left. And, you know, whether it's in joules or kilojoules is not important. Just to be aware of significant figures. Pay attention to the significant figures. These are acceptable final answers for this particular problem. Heat of vaporization in this problem was given at 2.25 kilojoules per gram, but also could have been given, or you could have used 40.5 kilojoules per mole by using the molar mass of water to be 18 grams per mole. So you have now looked at these heating curves, and we've looked at them conceptually in Thermochemistry 5, and in Thermochemistry 6 now we've done a mathematical computation to be able to explain and quantify what is occurring during a phase change. I'll see you guys in class.